Hello, and thank you for joining the webinar today. We're going to give folks another moment to log in. We'll be starting soon. So we'll give it another couple minutes. Thank you. Okay, let's get started. Hi, everyone, and welcome to today's Better Buildings webinar, dedicated to bringing you the latest actionable insights from leading industry experts. Better Building webinars are a chance to explore the topics, technologies, and trends that affect your organization, as well as efforts to accelerate energy efficiency strategies and reduce costs. So today's webinar is called Too Hot to Waste, Turning Heat into High Impact Savings. Before we dive in, there's a few housekeeping points I'd like to cover. Please note, today's webinar will be recorded and archived on the Better Building Solutions Center. We will follow up when today's recordings and slides are made available. Next, attendees are in listen-only mode, meaning your microphones are muted. If you experience any audio or visual issues at any time throughout the webinar, please send a message in the Q&A box located on the bottom of your Zoom panel, and our tech support team will be in touch. As for myself, my name is Prakash, and I'm your moderator today. I am a scientist, and I head the Building and Industrial Applications Department at Lawrence Berkeley National Laboratory. At Berkeley Lab, I support the Department of Energy's efforts around energy efficiency and productivity within the manufacturing sector, working on several programs such as the Better Buildings Program, Industrial Technology Validations Program, which you'll hear about in just a few, 50,000 Ready, and a variety of other programs. So I'm very happy to be moderating this session today. We got a great panel, and it's going to be a really important topic. So thank you all for joining. Okay, so as far as agendas, in today's webinar, we'll talk about how Better Buildings and Better Plants partners are turning waste heat into a valuable energy asset. Panelists will share strategies for recovering heat from industrial processes, HVAC systems, and commercial operations, unlocking significant energy and cost savings. But first, let's do a little poll just to get to know each other and just to loosen up a little bit here. Okay, so today we'll be using an interactive platform for Q&A polling called Slido. You can see if you go to slido.com, and if you've been on a Better Buildings webinar before, this is old hat for y'all. But if you head over to slido.com on your mobile device or by opening a new window in your browser, you can then pop in today's event code, which is DOE. And you could use Slido to ask our panelists questions, and you can submit those anytime throughout the presentation. We'll be answering your questions towards the end of the webinar, so we're going to hold questions until the end, and we can pull them from Slido. And one cool feature about Slido is you can select the thumbs up icon for questions that you like, which will result in the most popular questions being bumped to the top, and then we can try to prioritize those most popular questions. Okay, so I think folks have already gotten started with the polls, but we want to learn more about you and your experience. So let's start off with a few polls. Please move over to Slido to respond to the following questions. And if you're having any issues, please message our tech support team by using the Zoom Q&A function. So the first question is, what sector does your organization represent? It looks like we have, give it a couple minutes. All right. Well, we have an awesome 370 attendees today, so that's pretty great. And we're about 50% response rate. So how about we go there? Industry looks like it's about a quarter of folks on the online room here. Contractors, consultants, about another quarter, and then a great mix with federal government and local government coming around 8%. Very cool. Thank you for that. Should we go to the next poll then? Okay, so the topic of today is waste heat recovery. So does your organization have a waste heat recovery strategy in place? Give us a minute or so too. All right. Well, the numbers are coming in. And it looks like about half of you do not have a waste heat recovery strategy in place. So you're at the right place. Hopefully you'll get some really great information from this webinar from a panel of technology and industry experts that can really maybe get your brain juices flowing around a waste heat recovery strategy. About a fifth of you are working on one, and 16% do have one. That's fantastic. And 11%, I don't know. Okay, I think we have one more question. Why are you pursuing waste heat recovery? Select all that applies. Are you pursuing, thinking about waste heat recovery for energy efficiency reasons and the cost savings that come with it, to reduce emissions, to improve the way your processes work and productivity, or perhaps hedging against future energy costs if you see electricity costs increasing or anything like that. Maybe waste heat recovery is a hedge against that for a more stable energy cost. So I'll give it a couple seconds here. All right, looks like we got a lot of our answers in. Wow. And of course, you can select all that apply. So should have mentioned that earlier, but I think you guys figured that out. 90+% of you guys are doing this for energy efficiency reasons, which makes a lot of sense. We know energy efficiency pays off, so that's wonderful. 60% for emissions reductions. Yeah, and half of you are thinking about this as a balance against future energy cost increases. So that's great to directly towards the bottom line. That's wonderful. And the process improvements are still a high percentage. That's really great. Okay, I believe that's the last poll question. Perfect. All right, so today we have three speakers. The first speaker will be Anand Varahala, who is the Director of Energy and Sustainability at Schneider Electric. And then we have, for the second part of our presentation, we're going to have two speakers, Suhail Akhtar, who is Head of Process Decarbonization at Amrise, which is a cement manufacturer, and Jonathan Candy, who is a Chief Revenue Officer at ATS. So thank you all for being here today. We're going to jump right into it. And our first speaker is Anand Varahala. Anand Varahala is the Director of Energy and Sustainability at Schneider Electric North America, leading their operational decarbonization strategy. He also serves as a global subject matter expert supporting supply chain sustainability initiatives and advocating for Schneider Electric externally. With over 16 years of experience, he has led energy management programs, implemented ISO 50001 systems, developed energy efficiency tools, and conducted assessments at various facilities. With my pleasure, I will hand it off to Anand to kick us off with today's webinar. Anand, take us away.
Thank you, Prakash. Thanks, everyone, for joining us today. Before I dive into the project and the details itself, I'd like to set some context. Schneider Electric has recently been ranked as the number one sustainable company by Time Magazine as well as the corporate Knights. And this doesn't happen overnight. In order to continue our 20 plus years commitment to sustainability, about 5 years ago, we launched our net zero commitment in alignment with the SBTi's corporate net zero standard, through which we aim to reduce our operational emissions within scopes 1 and 2 by over 90% by the end of this decade, and value chain emissions, including scope 3, by 90% by 2050. So, as Prakash mentioned, my focus has primarily been on scopes 1 and 2. And with that, we'll dive into a bit more detail. So, if you look at how we aim to achieve net zero by 2030 within our own operations, we've had a long standing program dedicated to driving energy efficiency in our operations. We have started an effort to electrify our facilities and processes to transition away from fossil fuel consumption. Paired with renewable electricity, we plan to achieve net zero within our operations by the end of this decade. Next slide, please. If you look at the scope 1 emissions within our portfolio, this is specific to North America, that's in my direct purview, by the way. Close to 60% of our scope 1 emissions come from mobile sources, our sales vehicles, our services fleet, and so on. And the remaining 40% stationary emissions are mainly driven by our manufacturing operations, our factories, whether that's industrial processes like painting, molding, epoxy coating, heat treatment, and so on, or the HVAC systems and other building systems to support our operations and to provide services to our employees, account for 38% of the overall scope 1 emissions, leaving a couple of percentage points, a small proportion for many of our regional offices spread around the region. So, moving on to the next slide, the challenge that we have here with regards to electrification, I'd like to highlight a factory of ours located in Lincoln, Nebraska. It's a 50 plus year old factory, been around for quite some time, a critical manufacturing operation of our portfolio that runs essentially 24/7. Their productions are down 2 days a year around Christmas Eve and Christmas, but otherwise the production's running basically all year round. So one of the challenges we had as we took up on the challenge to decarbonize this facility is how do we do it with minimal disruption to production? That was the big challenge. Secondly, being a 50 plus year old factory, we wanted to ensure that the infrastructure that we had at the factory could support decarbonization without posing some significant challenges to us. The factory has historically relied on two large steam boilers to provide the comfort heating needs, served by 20 plus air handling units that rely on steam coils for heating and chilled water coils for cooling. We also had around shipping and receiving areas a suite of steam heaters as well as infrared heaters to support it. So, in addition to the challenges, we wanted to tackle some comfort related issues that the plant employees have been experiencing over the years. Next slide, please. So we could take the easy route, but we chose not to. We intentionally decided not to go for a simple like for like boiler replacement and replace our gas boilers with electric boilers, despite the technology being very mature, taking into account the fact that we could potentially significantly affect the operation costs of the facility. So what I have on the right hand side shows the spark ratio of our facilities within North America. Of course, the information is anonymized, but if we look at our operations, Schneider's own operations, when we look at the ratio of the cost of electricity to the cost of natural gas, it ranges between 2 and 7. Meaning, when we decarbonize, if we want to minimize the impact of our operating expenses, we'll have to improve the efficiency of our solutions by a factor of anywhere between 2 and 7. So this was another challenge that we took upon and worked with carefully identified partners to develop a solution, which I will go into further detail in the next couple of slides. Next slide, please. Yeah. So through one of the Department of Energy webinars, I came across World Energy Innovations, whom we have further explored through uh, interaction at an AEE conference, and we were really encouraged by the solution. And I'll briefly describe that here. So at the Lincoln plant, as I mentioned, we have large manufacturing operations. We have heavily automated assembly area that is supported by close to 5 to 700 horsepower worth of compressors. We have a third of the plant that is dedicated to injection molding that produces significant amounts of heat. And we also have brazing operations, all of which are connected through a central process cooling loop to extract heat away from these processes. And until last year, we've been dissipating that heat through the cooling towers. While simultaneously, we had, as I mentioned, two large central gas-fired steam boilers producing 380-degree steam to provide comfort heating needs for the facility. Now, there were some other processes that relied on steam, which have sort of gone away from the facility over the years. But before we started on this project, comfort heating was essentially the only requirement for steam. WEI brought to us this notion or challenge, saying if you're trying to maintain 70, 71, 72 degrees in our operations, why do we need steam at 300, 400 degrees to meet those needs, right? So that's how we started down this path. So WEI proposed to us a low temperature hot water solution, and to maximize recovering waste heat that we have been dumping into the atmosphere through cooling towers. And thirdly, to address some of the comfort related concerns, we wanted to maintain as close to neutral or slightly positive pressure in the building, given the large amounts of exhaust that we have in our process areas like brazing, injection molding, etc. And realizing that by addressing exhaust and maintaining the building pressure, would be able to eliminate large amounts of uncontrolled infiltration, particularly in areas like shipping and receiving docks, where we had the most comfort related concerns. So, partnering with WEI to develop the overall engineering solution, Control Services, one of our partners in Nebraska, to integrate the building automation controls into our building automation system, and NIFCO Mechanical for all the mechanical and other work, we were able to implement this phase one of our electrification project and reduced our operating expenses by over $100,000 per year, which was a huge success. We also reduced our gas as well as water consumption at the facility by 60% because we're now not relying on evaporative cooling all year round to extract heat from these processes, which resulted also in a scope 1 greenhouse gas reduction of 360 tons. And all of this led to us winning the 2025 Better Project Award by the Department of Energy Better Plans Program. Next slide, please. So if we dive into some of the challenges we faced, this was definitely by no means an easy project. Due to the critical nature of the production, we had to carefully plan all the work involved, be it changes to the air handling units or the plumbing infrastructure, to ensure that we were minimizing production. So, communication, early engagement of all the key stakeholders, and aligning the expectations, the project schedule, very close attention to the timeliness of the execution were super critical to ensuring success and making sure we did not disrupt production operations. I'll let you read the quote by the plant manager that shared with us at the conclusion of this project. Additionally, the novelty of the solution was a challenge that we had to overcome. We have not implemented a large scale heat recovery solution before, and we were not familiar with meeting our HVAC needs with low temperature hot water. And we had to spend quite a bit of time educating, getting into the details, and understanding the solution thoroughly, providing assurance to our operations folks and our facilities maintenance teams at the site to convince them and give them the confidence that the solution could work. So we leveraged existing air handling units and diverted the low temperature hot water through the chilled water coils, understanding that chilled water coils are designed to be significantly larger with higher surface area to maximize the heat that we're able to put into the airstream. We had to overcome some older habits as well. Uh, I talked about the exhaust and the negative pressure in the building, and oftentimes, especially during shoulder seasons, employees in the dock areas or in the mechanical room were in the habit of leaving the overhead doors open to let some of that air in. And that posed a direct challenge to our ability to maintain pressure. So we had to again implement a communication campaign, raise awareness about the solution we've implemented, and ensure that we had practices in place to keep all those doors locked and control infiltration into the facilities. Needless to say, over the last 18 months of this project implementation, we had to deal with varying lead times and other externalities. To sum it all up, I'll say identifying the right partners, very, very effective and timely communication with all stakeholders involved are probably the most important lessons I'd like to share with the audience here. And last slide. A couple more snippets I want to share with regards to the results. I'll highlight two aspects here. The top right hand chart depicts that over a very broad temperature range, and we're talking in Nebraska, where we go to negative teens in the middle of the winter, we were consistently able to maintain positive pressure in the building across a broad temperature range. That was a huge success. And you can see the impact on that in the two comparison charts on the left hand side, where previously, before the implementation of this project, our dock areas were experiencing temperatures as low as 60 degrees, whereas after the execution with tighter building pressure controls, we were able to raise that to 72 and make it consistent across the overall facility. That's all I have. Thank you. I'll pass it back to Prakash.
Wonderful project. Thank you, Anand, for that great presentation. Hey, a quick reminder to you all send in any questions you have at www.slido.com. Again, the event code is DOE. You can pop that at the top of the website there. I already see a handful of questions coming in. If you don't have, pop in your questions, but also remember you can upvote a question. Give it a thumbs up. That helps me know that that question is of interest to more than just one person, and we could do our best to ask it during the Q&A session, which will come at the end. Okay, and with that, I'm actually up for a little bit of an intro for to set the stage for Suhail and Jonathan's presentation in a couple of minutes. So again, I'm Prakash Rao for Lawrence Berkeley National Laboratory, and as part of that, as I mentioned, I work with our team here at DOE to execute a program called Industrial Technology Validations. So what is this program and what are field validations? You're going to hear a lot about it from Suhail and Jonathan in a couple minutes. So we thought we'd give you a little bit of a little table setting here to prep for that presentation. So field validation. So as you think about a technology, it goes through its life cycle or its birth, let's say. Maybe it's a concept that some smart people have. And they'll work the physics out, make sure it works. Then maybe it goes to a lab scale and it's demonstrated, and they prove it at a lab scale, and then maybe they build it up a little bit bigger at a larger scale. And it kind of keeps going through these iterations, the technology going from theory to practice all along the way. And at some point, it's out of the R&D world. The labs and the researchers have done what they can to kind of say, hey, I think this thing's ready. You need early adopters then to say, hey, that's an interesting technology. I haven't seen that before. I think it could help my plant or my facility achieve my goals, and I'll take it on. Unfortunately, there's risk, of course, involved for those folks who are looking to take on that technology, as they're the first adopters. The performance of that technology isn't necessarily um, well known. They can't go online and learn about it. They can't go to their colleagues and ask about it because there's not a lot of information out there. And we call this that gap between the technology ready to be commercialized, ready to be go out into facilities, and out there for someone to go get readily. A valley of death. A lot of crossing this can be kind of difficult for technologies at times. So what does field validation do? Field validation is intended to de-risk for that for those adopters the information gap, right? So by implementing a technology at a pilot scale or a pilot plant, and then doing robust testing of that technology in the real setting. So it's no longer in the lab, it's in the real setting, delivering real performance, and being able to demonstrate that helps others understand, okay, this has been done. It's a little bit less risky. I have a little bit more information on what to expect. And that's field validation. And that's the gist of the industrial technology validation program. Accelerates commercial, the benefits of it are to accelerate commercialization, mitigate technology adoption risks, and enhance your confidence as industry in picking up that technology and trying it at your facility. Next slide. So industrial technology validation program, it's premised around that exact value of death problem. So a tech provider, in this case, you're going to hear from ATS, and a site, in this case, you're going to hear from Amrise, apply to the Department of Energy's Industrial Technology Validations Program, saying, hey, we want to test this technology out. We need some field validation to see how it performs. And through a competitive process, they're selected, and DOE lends over national lab expertise to conduct on-site testing, conduct what's called M&V analysis, of measurement and verification analysis, and draft reports validating these field, the performance of the text results and the real-world environment, and publish them. So M&V, measurement verification, for those who are not familiar, is a very rigorous process where involves installing the technology on site and collecting information, data, lots of data before the technology is implemented, and then as it's implemented, and then using statistical analysis to adjust for any factors affecting performance that wouldn't be related to the technology or energy, for example. So perhaps production schedules or what might have been produced during those 2 periods of time, correct it so it looks consistent, and then compare that across the two to understand the energy savings. It focuses on what you might expect from implementing that technology at your plant, with the huge caveat, however, that your performance will be your plant specific. But here is what we saw purely based on the technology's performance within this one site. So the ITV team then also used that M&V analysis to project what this technology could mean for the greater industry in which it's adopted. And we share this information publicly, hoping that all will benefit from it. Next slide, please. So some of the barriers that we're trying to look at here is uncertainty in real-world performance and viability, lack of critical independent performance data, unclear scalability costs, and broader system-wide impacts with these technologies that are about to emerge, that are pre-commercial, emerging, ready to be commercialized. So we have these barriers. If it's animated, so the next slide, or hit the cursor, please. Yeah, there we go. So the methods applied. Again, it's using the M&V, the measurement verification process, in a real-world setting to validate the performance claims of the technology, and then publicizing it so others can understand. Next click, please. And so what we believe ITV is going to provide is credible validation of the performance of the technology to help increase market acceptance and to help de-risk, again, for that next person adopting that technology by providing more technical information. Next slide, please. So to date, there's 5 reports available, with the 6th coming soon. So we've done field validations at Toyota, Nissan, Alstom, Munksjö, Cleveland Cliffs, Amrise, which you'll hear about today, and Stryker. You can read a little bit about the descriptions there, but there's water treatment systems we've looked at. We've looked at membrane separators. You can hear about a thermoelectric generator. We looked at advanced motor systems and controls for those motor systems. And if you go to the next slide, well, here's the team. It's not just me. I'm just one of many, but it's a joint effort between Department of Energy, Lawrence Berkeley National Laboratory. And these are some of the experts that if you join the ITV team, you'll be able to connect with. Next slide, please. And finally, here's if you are able to scan that QR code where it says ITV Validations Library, you can go check out the reports. Stryker is coming soon, but the other 5 you could check out at the ITV Validations Library. You'll find a report there, and then you'll find a 4-pager, which is a little bit or much less a slimmer version of just the facts for the validation. I also want to let you all know that we are gearing up for a new solicitation. You can learn more either at the team page or at the email signups. Those new solicitation is really exciting. We are constantly trying to improve the program and are adding financial incentives to help defray some of the risk for the companies and the technology vendors as they validate this technology together. So there will be a cost share requirement, but that's a new component where we're looking to help kind of sweeten the pot a little bit to help folks offset any sort of costs associated with adopting new technology, being the first adopter of technology. If you're interested, industry technology vendors on the horn right now, click the QR code right there and you can sign up for a teaming page, and what that'll help you say is, hey, I'm a facility, I'm interested, and if there's technology that comes across our books that looks like it could be a match, we could try to see if there's a match there. And please sign up for emails and you can get updates. And at any time, ITV support at lbl.gov. Feel free to email us. We're happy to answer any of your questions. So with that, I will kick it over to Suhail and Jonathan. So Suhail Akhtar is currently working for Amrise. Suhail has over 30 years of cement manufacturing experience. He has managed and supported process, quality, and operations optimization for multiple plants. He initiated and implemented numerous process engineering and technical learning and development programs. Suhail has participated in the commissioning and startup of several greenfield and brownfield cement plants. He also headed the energy management program of companies' all North American plants for 8 years. And over the past 4 years, his work has mainly concentrated on the post-combustion carbon capture industrial decarbonization technologies. So Suhail will be representing Amrise, who tested out the technology at their facility. And now representing a technology company, ATS, is Jonathan Candy. And Jonathan is a technology and business executive with a proven track record of driving growth, scale, go-to-market strategy, and defining new quadrants globally in B2B markets. Hands-on leader building teams with vision and a drive for execution as part of culture and a shared success. He has technical acumen to strategize concepts with technology, engineering, and product teams, resulting in business solutions to enable enterprises. ATS is Jonathan's 5th startup with a successful IPO and unicorn in his previous tenure. So with that, I will hand it over to Suhail, who will speak about on behalf of Amrise, and then he'll hand it over to Jonathan, and then we'll go from there. Suhail, take us away.
Thank you, Prakash. Thank you for the kind introduction. And I also thank you, Department of Energy, for inviting us to speak in this webinar. The title says, too hot to waste. I would say it's too valuable to waste. I don't know about many other industries, but I know about cement manufacturing, where I have spent the last 30 years, that the energy cost for us, the thermal energy or electrical energy, constitutes a significant portion of our total cost. Sometimes more than 50% of our variable cost, and maybe 25% or so of the total cash cost for the manufacturing. So it's a significant amount of money that we spend on energy. So if there is any improvement in specific electrical energy consumption that we could achieve, or specific thermal energy consumption that we could achieve, that will bring lots of saving for us. And like good environmental folks say, reduce, reuse, and recycle. The first action on our part and in our industry, in our plants, is that we look into the possibility of reducing the consumption, reducing the wastage. But then when it comes a time or a point that we cannot do it any further, then we look into the opportunity to use or reuse the wasted heat or energy that comes out of the system of the plant. So can you go to the next slide, please? So I'll give you the background of this project, and I will just give you the general information about the cement manufacturing process. But as far as the technology and the testing of the pilot is concerned, Jonathan will provide you the details of that. So the background of this is that, like I said, a significant amount of industrial energy input goes into the waste, and that waste could be in the form of hot surfaces or cooling water or hot gases, exhaust gases that leave the system. Many industries are very energy intensive, steel, glass, but my industry, cement industry, is really energy intensive industry, and there is a significant portion of the total thermal input that we put in to the system is wasted in the form of hot gases that leave the system and so on, that I will describe in the next slide. So industry has been trying to recover this wasted heat for quite some time. Around the globe, if you look into it, the waste heat recovery systems are prevalent, and in many places where the cost of energy is really, really high, it becomes more important. In the US, it is picking up. There are techniques that are in place, steam Rankine cycle, organic Rankine cycle, combined heat and power, and so on. There are different ways to recover heat or wasted heat. Now, thermoelectric generator that we are discussing in this presentation, that can be used to reclaim the wasted heat, and with this intent to test this methodology, we provided our plant in Alpena, Michigan, which is in northern Michigan, as the host site for this pilot study that was done by using this TEG technology by ATS. So the details of this will be provided by Jonathan. I will just give you the details of the cement manufacturing in general for where the wasted heat comes from. So can we go to the next slide, please? So for cement manufacturing, if you look into this, this is the slide for a relatively efficient cement plant. And even here, if you look into the thermal energy input or electrical energy input, it is significant amount of energy that goes into cement manufacturing. But the interesting thing is that only 55% of the total heat input in the cement kiln is really needed for the clinker formation, the product that we make in the cement kiln. The other is wasted in the form of either hot gases coming out of the preheater. And if you see on the left-hand side, there is a tower, the preheater, the cyclones. The material, the raw material, as it goes in and is preheated into the preheater before it goes into the kiln. The hot gases that are leaving the system, they leave somewhere anywhere between 300 to 400 or even higher than 400 degrees. And then the clinker that comes out of the kiln on the right-hand side, and it goes at very high temperature into the clinker cooler, which is used to preserve the characteristics of our clinker or the material that we make. The air is used to cool down this clinker, and whatever we can recuperate in the kiln, the rest that comes out or is expelled out of the cooler comes out also at very high temperature, anywhere between 250 to 350 degrees C. So if you look into it, somewhere around 30 to 40% of the total heat input is wasted. Now, this waste heat is also dependent on the type of process and the issues in the process. Like we have to, in some cases, maintain the temperature above certain to prevent the dew point. And then there is drying requirement internally that we have to utilize. If we have a waste heat recovery system, we have to keep in mind that that is also slave to the cement plant. If the kiln goes down, then the system also goes down with it. So can we go to the next slide, please? So as I said, 30 to 40% of the total heat input in the system is wasted through the hot gases, either coming out from the preheater or from the cooler in the form of radiation from the hot surfaces and so on. In terms of waste heat recovery, that has been looked at for cement manufacturing. And this is other than the thermoelectric generator that we are talking here. In the past, there have been and still in use for steam Rankine cycle or organic Rankine cycle and so on. Basically, the methodology is the equipment that we need is a heat exchanger that takes the heat, and this heat exchanger is next to the preheater tower. This heat is taken out of the hot gases and is utilized to generate steam, which later on, if you see in the middle on the top, to generate to run the generator to produce electricity. So basically, the component is the heat exchanger, the generator, and then a cooling system to reuse or to cool down the steam, the expanded steam, which is used to generate the electricity. So basically, with that, I pass it on to Jonathan to take us through the ATS pilot at the Alpena plant.
Thanks, Sahil. So first of all, we're talking about a thermoelectric generator. We've kind of started to call ours as a whole a solid state generator, pulling from the idea that we all remember using spinning disks in our laptops, and we moved to SSDs in the same way that turbines now can be solid state generators. So at ATS, we spent the last 10 years developing this product set. We've taken bismuth and tellurium and doped this with additional minerals in a very specific formulation for a positive and a negative semiconductor material. We take that material, we put it through an SPS process, which is think heat and pressure, to drive a specific formulation of our semiconductor material. We then metallize that and cut that into pellets. Those pellets are then put inside of a cartridge. I'm actually holding one up right here, about the size of an iPad mini. Those are stacked between a hot and a cold plate. Sahil just talked about the heat exchanger. That heat exchanger can pump either steam or thermal transfer oil into the hot plates. The cold plate is room temperature water running on through. We've packaged these into an industrialized shipping container format to deliver to industry. Next slide, please. Inside of the pilot unit that we built, you can see on the right-hand side the hot and the cool coming on in. And then these are brought into what you see in the bottom left, which is the cartridge array of the hot and cold plates with our cartridges in between. Next slide, please. So what we have here is a 20-foot long, 8-foot wide, 8.5-foot tall shipping container. We put 582 total cartridges into this unit. Our ideal temperature for maximum efficiency is 240 degrees Celsius. We see really generation starting anywhere in the 150 range up, and our ideal temperature, though, for maximum is that 240. That is designed to drive about 20 watts per cartridge at that temperature, and that's our ideal scenario. We used a portion of the waste heat from the kilns at the Amrise facility, formerly Wholesome. Amrise provided us this existing steam. We then turned that into a transfer oil that was able to be pumped across our hot plates for operation at 150 to 240. Luckily, we had Lake Huron right by, so we used that for the cold water source in the cold plates. Next slide, please. So what was the output? We were able to run this test and across a wide range of temperatures. As I said, we were all the way down to 130. Unfortunately, we didn't get up to the full 240 C. We were at 212 was the high end. But the average, and that average, as the DOA puts it, cuts off the top and low performers to develop kind of that mean in the middle. And we ended up with a wattage of about 15 watts per cartridge, with some actually reaching 35 watts. Across this, what we see is a heat exchanger at that facility with our thermoelectric generation or solid state generator, driving about 391 kilowatts of net power. Across the industry and across the 96 cement plants that were looked at in the United States, we saw this as obviously a very viable technology for this low to medium temperature heat waste, with really applications that the DOE called out, including glass, cement, steel, aluminum, metal casting. Next slide, please. So our takeaways from this, this was the first commercially ready solid state heat to power generator put in place in a real world setting. We've now tested this at the oldest plant in the United States. It's been in operation for over 100 years. It's the largest cement plant out there. You can see in this picture on the right, the hot and cold plates with our cartridges stacked in between. The demo outperformed. The target was a 5% net efficiency at 240 C. Obviously, we didn't even get to that, but we actually outperformed that significantly. We also, since this has taken place, have found use cases ranging all over the place. Ultra-low sulfur diesel streams. You have the oil sands upgraders, gasification units, thermal oxidizers. We've started to look at integrating with geothermal, biodigesters. When we hit higher efficiency levels, we actually see direct-to-chip cooling in data centers as a future potential as well. We have now hit a 14% maximum with a product roadmap heading towards 25. And there you go. I think we're ready for Q&A.
Oops. Oh, great. Thank you very much, Jonathan and Suhail. Yep, we're almost ready for Q&A. Just a couple other items. So one more item. So first of all, thanks all to the panelists. Thank you, Anand. Thank you, Suhail. Jonathan. Thank you, Jonathan, for your wonderful presentations and your insightful presentations. Before we transition to Q&A, though, I want to encourage you to download our additional resources handout shared in the Zoom chat box. You could see that right there. The handout contains links to resources from Better Buildings and our speakers on today's topics, and we hope you find this useful. So we'll move over to Q&A right now, and we're going to use Slido as our sort of organizing structure here for the Q&A. If you haven't already, you can hop over to slido.com, type in DOE at the top for the event code, and you could submit and upvote questions. It's not too late. Questions are still coming in. You can still upvote. And as you guys get going, we got a good set of questions here, so why don't we get started? So the question, and I think it probably came in during Anand's talk, so it asked specifically, how does Schneider Electric fund decarbonization projects? So Anand, we'll start with you. How does Schneider Electric fund decarbonization projects? Suhail, and from your experience too, would be wonderful. And Jonathan, on the other side of things, if you have any sort of thoughts on how folks are funding these projects, that'd be great to hear. But we'll start with Anand. How does Schneider Electric fund decarbonization projects?
Certainly, Prakash. I've provided a couple of comments within Slido, but I'll add some more context to it. So within Schneider, as I shared earlier in my presentation, we have an ambitious target by 2030 of reaching net zero within our own operations, scopes 1 and 2. And we've gone through an effort internally to calibrate with our XCOM team and identify CapEx funding for decarbonization initiatives. So the short answer is we've used our own CapEx. However, on a project basis, as we go through the process of evaluation, justification, funding approvals, etc., we do consider OpEx or energy as a service models as well, and evaluate the projects on a case-by-case basis before we approve or finalize the funding criteria.
Fantastic. Suhail or Jonathan, anything from your perspectives on how best to fund decarbonization projects?
Once again, yeah, we are currently in the process of evaluating and assessing different technologies for decarbonization. And basically, cement industry is a little bit of a latecomer in this, but we are following exactly the same procedure for which technology that we can apply, and then look into the potential cost of it and see if we can make the arrangement for that, and how would we do it, apply it in our plants.
Yeah, I'm happy to jump in. We're happy to work with teams. We have built our solution as energy as a service, so there's a potential to even have a no upfront cost depending on the model that you're looking for. We would look to actually fund that and drive a 10-year PPA over the life of that 10-year agreement with a rate structure we're aiming to try and beat the utility by about 10%. That's our goal at ATS. So luckily, we in the United States, if it's put in place and deployed in the United States, we do have a North American supply chain and 48E, and as continued on from a net zero perspective in the latest big beautiful bill, while wind and solar fell out, heat to power is still in there, and ATS certainly is happy to take part in it.
Wonderful. And maybe another follow-up question specific for your project. Was the utility any support? Were you able to talk with your utility and get any support from this or any other decarbonization project you might have implemented?
That varies quite a bit from state to state. We partner with one of our own internal consulting organizations to evaluate the utility incentives, but for this one in Lincoln, Nebraska, unfortunately, there were no incentives available for us.
Understood.
Yeah.
Well, we got another really great question. I love this question. So I think this goes across the board. Do you guys quantify the non-energy related savings to justify the projects? And you already spoke about the employee comfort, but I wonder if you can kind of go deeper, and Sahil and Jonathan, any non-energy benefits. It would be wonderful to hear about.
Qualitative analysis for certain to identify, like I mentioned, comfort-related issues and air quality issues, particularly for the Lincoln project. We've qualitatively identified and highlighted those in our business case, but we did not, honestly, bother trying to quantify them because that can get quite a bit tricky. Questions about assumptions and how do we quantify, so on and so forth. So, short answer, quantitatively no, qualitative identification, absolutely.
And Sahil, maybe generally from a cement plant, how do cement plants think about non-energy benefits? Or how does the cement industry think about non-energy benefits of projects like these?
Well, okay, so taking the cost element out of it directly, you have to see the impact of it in the CO2 reduction, scope 2 emission reduction directly, and there is a cost associated with that. So for any energy project like this, even if we are using this one for electrical energy generation or reduction in thermal energy consumption, we look into the direct impact of how much CO2 we will be reducing and what is eventually the impact of that in terms of savings.
Jonathan?
Carbon credits. I mean, there's a carbon credit. We can certainly develop. Every deal is different. I look at that and say that's a negotiable item, whether we're taking the carbon credits or you're taking the carbon credits. But at the end of the day, those can be upwards of 20% of the overall cost of a unit. From our standpoint, the other piece is that hedge. I think you had it in one of your questions. I guess it is still energy related, but I mean, you look at all of the statistics are pointing at data centers, especially AI data centers, driving a significant, we'll call it pain point to the grid coming forward. I don't know what that's going to do, but certainly that hedge aspect against what could be a tightening availability of energy.
Absolutely. Wonderful. Yeah, thank you. The next question, we'll keep it on you, Jonathan. It's a very specific technical question. So the question is for Jonathan. Glad to see that the new technology is used for electricity generation. What is the conversion efficiency of the solid state generators?
Sure. So in the pilot that we did, I believe it was an 11% efficiency from a thermal efficiency perspective. As I mentioned on that last slide, ATS does have a max efficiency today of a 14%. The trial was about a year ago. We're continuing to improve. But yeah, you can count on the 11 and upwards of 14 with a roadmap as we continue to change, driving that towards 25, 30.
Awesome. That's great to hear. Let's see. Well, I'm familiar with Schneider and Amrise's energy efficiency benefits or efforts beforehand. So this might be a softball for you guys, but do you do any energy efficiency improvements such as building envelope before implementing? In this case, I think none of those to you, new hot water-based heating, but I guess more generally for both your companies or in your experience, that order, do you do energy efficiency first and then these projects? How does that work? What's the priority in pecking order here when you're thinking about projects?
Okay.
I can go for it.
Yeah, okay, go ahead.
So for us, Prakash, as you said, it's a very softball. We've had an energy efficiency program at Schneider, particularly in North America, for close to 20 years now, a little over that. So we've had a well-structured program where part of which we conduct comprehensive energy assessments at roughly a third of our facilities every year on a recurring basis, identifying energy conservation measures, and we have a process through which we prioritize those ECMs, secure funding, and implement them. So since we've been doing that for an ongoing basis for quite some time, specific to this project, we have implemented several energy efficiency improvements, as well as building envelope improvements like roof replacement, adding further insulation to the roof to bring it up to current energy codes, and so on, before delving into decarbonization. So the last 5 years and the next 5 years, I'd say there's going to be an increased emphasis on electrification and decarbonization to help us get to that 2030 net zero target. But the underlying energy efficiency program will continue to be a priority.
And so, okay, kind of more broadly in the cement industry, how do they kind of order these?
So for the past 15 years or more, that in fact I was personally involved in the energy assessment, energy kaizens, and we are part of Better Building program, the DOE's Better Building program, where we achieved the objectives. The energy efficiency improvement internal program, energy audits, are a part of the routine for us. Like I said, first effort has to be made into reducing it. So we look into all those possibilities where we are resulting in consuming higher energy, false air reduction, like I think Anand brought that up, false air reduction and so on. So we have that as a consistent program as one of the levers to look into. Then we have the alternate fuels and raw materials as the resource to replace the fossil fuels as a constant, consistent program for us, internal effort. We have an ongoing effort internally to reduce the production of high CO2 generating clinker and replacing it with the mineral component and supplementary cementitious material, calcined clay, and so on. So there are internal programs, which we're looking up as the first priority to achieve the objective before we go into the actual post-combustion carbon capture and so on.
Mm-hmm. Excellent. And I encourage all, one of the many great things about the Better Buildings program is our partners share so much information about what they've been up to. So you could go check out their partner pages. I'm sure we could pop a link in here, or if not, just Google Better Buildings and Schneider, Better Buildings and Amrise, and you can go see both companies that provide a lot of information about their historic achievements, how they've achieved them, and you can go check that out. So we're almost at the top of the hour, and I do want to get you out of here on time, virtually out of here on time. So why don't we just do some closing last minute some closing housekeeping here. So thank you everyone for your questions, and thank you especially to Anand, Suhail, and Jonathan for their insightful responses to the Q&A. This webinar is part of the Better Buildings 2025 summer webinar lineup. As you can see, we have a great collection of presentations through the end of the summer. Visit the Better Building Solutions Center to learn more and register. And our next webinar is on August 19th. It's called HVAC Hacks, Accelerating Small Building Efficiency with Improved Controls. In this webinar, you'll hear from leading organizations about how they harness the power of smart thermostats and advanced building control. So you can register today, and again, that's on Tuesday, August 19th at the same time. And in closing with that, I'd like to thank our panelists again for very much taking the time to be with us today. I'd like to thank you all for joining the webinar and taking time out of your busy schedule to hopefully learn something new. Feel free to contact your presenters directly with additional questions, or if we couldn't get to your question during the Q&A period, just feel free to reach out. I encourage you to follow the Better Buildings Initiative on LinkedIn and X for all the latest news. You can find our handles by the respective icons on the left hand of the slide. Yeah, there you go in the blue. You'll receive an email notice when today's recording, slides, and transcript are available on the Better Building Solutions Center, so you all will be getting the slides. And with that, let you out here a minute early. Thank you, everyone. Have a wonderful rest of your day.